Okay, so the amazing thing that you just saw there, that was talking about conduction here. So let's go and develop conduction. The equation of conduction was developed by observation. So this law was developed by observation. Okay, and so you need to understand the difference between heat transfer and temperature again. You know, heat transfer is because of a temperature difference, because there's a delta T, a temperature gradient. All right, transfer of energy happens from more energetic particles to less energetic particles, and this is a diffusion of energy. So we'll use the word diffusion here. We're diffusing energy. Now we're going to talk about conduction, and conduction is going to be between solids, is inside of solids. It can occur in gases, and we'll talk about that later. It can occur in liquids, but mainly when we talk about conduction, we're going to be talking about that in solids. So we're going to look at a wall or a plate to start off with. And so let's look at a one-dimensional wall. In heat transfer, you're going to deal with two-dimensional, three-dimensional walls, of course. So here is our wall, and we're going to say that there's going to be some temperature 1 here, and there's going to be a lower temperature, temperature 2 in this wall. All right, just any wall behind you, whatever is happening. We're just looking at this one dimension. We're looking at this x dimension here. Okay. Now, if T1 is greater than T2, we know what's going to happen. We know what's going to happen. We're going to have heat transfer that's going to go this direction, and we're going to call that Q dot conduction. Now, why am I saying dot here? Because we want to look at the rate of heat transfer. Q dot of conduction. We know that heat's going to travel from 1 to 2 in that direction. So if we look at what our law is, it's going to be Fourier's law. Of conduction is what we're going to develop here. Okay, it's the rate of heat transfer. So Q dot conduction. So this is going to be the rate of conductive heat transfer is equal to. Now, what are some things, and think about that experiment that we showed, what are some things that change the rate of conductive heat transfer? Okay, so we had those two plates, and we knew that one was made of metal and one was made of a plastic or a wood. So the material property had something to do with the rate of heat transfer. And so there is something called K, and I'm going to make a fancy K here, called the thermal conductivity. Easy to remember because thermal conductivity doesn't have a K in it, so we're going to use K to determine thermal conductivity. Okay, so thermal conductivity is a property. Every material has a thermal conductivity, and in your appendices, you're going to find a list of all sorts of thermal conductivities. Okay, and that's going to be in table A19. A19, and let me just see if I can't. Let me right here. A19 or A19E. And let me just make sure, does my document camera want to work? It doesn't want to work today. My document camera, I'll have to show it to you. Here it is. Here is the table. Thermal conductivity is right there. All sorts of thermal conductivities for all sorts of different materials. Now, the one thing you need to know is that it is a property, okay? And we have it in one page in our appendices. You're going to have it in. You can have whole books that talk about the thermal conductivity of various different things, so we can see those. So it's a property. You don't have to worry about that. Let's talk about what else determines the rate of conductive heat transfer. Well, you are going to have more heat transfer if you have a larger area. So the next thing we're going to talk about here is area A. Okay, and this is going to be a surface area. So this is again why you must know, and make a note here, you must know the area of circles. You must know the area of a square. You must know the surface area of a cylinder, the surface area of a sphere. You must know that. I trust that you know this. This is always something, though, that surprises me about students that don't know, and I don't have it on the equation sheet. I'm not going to give it to you on the equation sheet. You must know these equations, okay? You have the talent and the ability to know that. Now, what's the hardest? The area of a circle, which is pi r squared, or pi over 4 times d squared. It is not 2 pi r squared. It is not pi dl. I mean, there's just lots of ridiculous things I see. Please understand what the surface area of different shapes are. Okay, sure, surface area. Okay, what's something else that determines about the rate of conductive heat transfer? Well, if you have a big temperature difference, if the temperature is like, if I go out to my barbecue grill and I start it up and it's at 500 degrees and I put my hand on it, there's going to be a lot of heat transfer there. If my barbecue grill is at 80 degrees and the outside temperature is 78, not a lot of heat transfer over there. So the temperature difference is going to make a difference. So we're going to put here dt, or T2 minus T1. This is going to be our delta T is going to be here at the top. Here, I'm going to put that. I should just write it as T2 minus T1. That is going to make it bigger. And there's one thing that has an inverse relationship with the with conduction, the rate of heat transfer, and that is going to be the thickness of the wall. A very thin wall, like let's just talk about a piece of paper, you have a lot of heat transfer through that. But if we make that wall bigger and thicker, you're not going to have as much heat transfer there. So we're going to say x2 minus x1. And this whole thing here, we can write this as dt dx, and this is called the temperature gradient. Something I've talked about before, the temperature gradient. If you have to have the bigger the temperature gradient, the more heat transfer that you're going to have. Now, what you might notice in this equation is temperature 2 is always going to be less than temperature 1. So this would always give you a negative number, and so we don't like that, and 4a didn't like that, so we put a negative sign right in here in the front of this to flip the sign, because again, T2 minus T1 is always going to be negative. So therefore, we are going to have our equation Q dot is equal to minus Ka dt dx, and that is the law of conduction. That's all we need to know. Now we have to plug and chug through this and figure out where it goes with. This thermal conductivity, it has units of watts per meter Kelvin, or BTUs per hour per degree R per inch. Okay, this is confusing, and there's lots of things going on here. Remember, a watt and a BTU per hour are very similar here, and now you're going to have meters and inches, they're related, and Kelvin and Rankine, they're both temperatures. This is the time where I will talk to you about units in the denominator. When we say per Kelvin, a unit Kelvin is the same as a unit Celsius. A unit of degree Rankine is the same as a unit of degree Fahrenheit. So even though we have Kelvin or Rankine in the denominator here, it does not matter if our temperatures are in Kelvin or Rankine. As long as they're in the same unit system, as long as they're the same SI, these are going to work for whatever. However, excuse me, I'm boring myself tonight. The thing you need to understand is that the delta T, it doesn't matter in this equation where you put this equation. So let me write it again. Q dot to minus Ka T2 minus T1 all over x2 minus x1. It doesn't matter if you put your delta T here. This delta T in Kelvin will work, in degrees Celsius will work. the same delta T is going to occur in Kelvin as in Celsius. And if that doesn't make sense to you, I want you to go and do some conversions and work with that. One of the most common errors students make on an exam is they will see that they have temperatures in degrees Celsius and they have units of Kelvin. It's going to be in watts, or sorry, units of thermal conductivity in watts per meter Kelvin, and they will convert from Celsius to Kelvin, and it's not needed. And in fact, it will mess your problem up. So you have to understand the units, you have to understand the equation for this for this easy plug and chug to work out, or else you're going to be in trouble. Now, I want to tell you on all exams, what I'm going to do is give you temperatures in Celsius or in Fahrenheit, because that's what we commonly deal with. You're going to have to understand the relationship between Celsius and Kelvin, between Fahrenheit and Rankine, to do the problem. My tip and trick here is that you never, ever, ever have a time when putting a temperature in Kelvin or putting a temperature in Rankine will hurt you. So if you are worried, should I convert or not? Always convert. That will, I can't tell you 100%, but that most of the time will keep you out of trouble. Okay, that's what I would say. Most of the time it would keep you out of trouble, but it does take some more time. So if you understand that delta, let me say this again, let me write this down, that the delta K is equal to delta C, and that delta degree Rankine is equal to delta degree Fahrenheit. If you understand that, you can save you some time on an exam. Okay, again, we're going to practice plugging and chugging here, and then you'll be good to go. So that is our first thing, conduction, our conduction equation.